Okay, here we are. Hi, everybody. Thanks for joining today, and welcome to a new episode of our machine learning seminars, machine learning security seminars. So today, as a speaker, we have Xin Chen from ETH Zurich with a talk on learning safety constraints for large language models. And for your information, this presentation will be recorded and uploaded to our YouTube channel, where you can find all the information about the seminars, such as future events and all the recordings from past events. In the same YouTube channel, if you are interested in learning more about these topics, you can also find a short course on machine learning security. So before we start, I want to thank the other co-organizers of this seminar series, and among them there is Giorgio, who will introduce today's speaker.
Thank you, Rafael. Hi, everyone. So today we have as a speaker Xin Chen, but you can call her Cynthia, which is a PhD student at ETH Zurich, supervised by Prof. Andreas Krause and Florian Trammer. So her research focuses on large language model safety and alignment, combining principal methods with empirical findings to make LLM safety mechanisms more trustworthy. Cynthia is also a fellow at the Open Philanthropy AI Fellowship and the Vitalik Buterin PhD Fellowship. So Cynthia, if you're ready, the stage is yours.
Thank you so much, and thank you for having me here. So let me share my screen. Okay, can people see it? Okay. So thank you everyone for joining the talk today. This is a paper that's recently published at ICML. As I just said, this paper is about learning safety constraints for large language models. And so in this talk, I will cover four major content: background, method, results, and future work. I might not fully cover the whole 1 hour. Maybe I will leave 10 minutes in the end, and I'm curious about any discussions, opinions, questions, or follow-up work discussions. I'm quite curious. Okay, so now let's get into the background. I hope by now that most people should, by now most people should have already seen that large language models are powerful tools, but safety is still a fundamental challenge. So someone can give a very illegal request to an LLM plus some jailbreaking suffix, for example, and then the LLM can actually give very harmful responses to that person. And so people have tried to mitigate this through different methods, such as RLHF, but it has also its own problems, such as reward gaming and also expensive training at the same time. And people have also developed prompt-based defenses, but they are all proved to be quite brittle by the more advanced adversarial attack methods. And I think a bigger problem is most methods are not really explainable to some extent. They lack interpretability, or they are not that principled, and do not provide further discussions on why we should trust them. So with these in mind, we started to look at LLM safety through a constrained Markov decision process perspective. So why this is helpful? Very briefly, I will go through, for those who don't know Markov decision processes yet. This is an overly simplified interaction graph. So we have an agent. The agent interacts with the environment by taking an action A, and the environment will give back a next state information and a reward R, this oversimplified MDP. And usually the goal for this agent is to maximize the reward. And so from our perspective, we want to find a policy that solves the reward maximization problem. So here T takes into account the matter of time. But the constrained version of this problem is to require that the final policy we identified is in a safe set. which the set is defined by the cumulative costs that incurred over time should be smaller than some threshold. And here, these thresholds are some cost budgets. So imagine you're in autonomous driving problem. Maybe you allow the car to go a little bit over speed, but you probably don't want to allow it to completely crash and cause severe damages. Okay, and it is quite common to study the language generation process with MDPs. So for example, the reinforcement learning from human feedback as a part of fine-tuning the language model and etc. So there are many previous work that are already adopting this reinforcement learning angle. And our framework is to ask whether learning such constraints from data is feasible and whether there are something interesting about it from a language and LLM safety perspective. Yeah, so one part of the motivation of this paper is a previous somewhat theoretical reinforcement learning paper, which asks the question whether we can learn safety constraints from offline data with unknown rewards. So basically with this framework, you don't need to learn, you don't need to already know the reward associated with each data, and you don't need online interaction with the environment, which is perfect for studying language models because we also don't assume that we have access to the ground truth reward of a sentence, and we don't, a cheaper way to train it is to not have it interact with actual human in the real time. But the main takeaway, the main association with this paper, with our work, is that it concludes that one can construct a safe set of policies within a convex polyhedron. So in this paper, if you're curious why this is a convex polyhedron, this paper provides a lot of good deductions to it. But for the talk today, you just need to remember that this paper basically says one can capture the whole set of safe policies in a convex polyhedron. So that is the theoretical motivation or observation of this problem. And we also have the empirical observation of this problem. So many of you probably are not unfamiliar with this diagram here, where it's from many years ago that people studied the word vector representations vectors. And they realized that the direction from men to women is parallel with the direction from king to queen. So this basically tells us that there probably exists a single linear direction that means gender. And similarly, there are many other directions of such linear directions discovered in the interpretability community in the past decade. And so very recently on language models, this phenomena is exposed again in some previous work on the linear representation on in the activation space of language models. So for example, there can be safety directions, linear directions about misinformation or fraud or child abuse. And one can think about, once you have a direction, a vector of meaning, you can also define a number, a threshold on which beyond this threshold, that's too much misinformation. And below this threshold, maybe it's okay to have a tiny bit of, or maybe even not detectable, non-detectable misinformation. And once you have a definition of direction and a definition of the threshold, you're basically recovering a polytope structure. That's all you need for defining a polytope. And so what we want, what defines a polytope is once you have the feature of a data, any feature, you can define a polytope through a phi and a xi over here. And that also describes our general direction or solution towards understanding the safety problem within language model, which is using this safety polytope geometric structure. So something can be like the prompt is to ask the language model to write some misinformation about the how Anthony Fauci was involved in the lab leak of COVID-19. And if it's an unsafe question, can totally start, an unsafe answer can totally start fabricating facts about writing a persuasive essay. But one can manipulate the language model such that it will say, I can't do this because it's false information. Okay, so far this is the main framework. The remaining question is whether this hypothesis this structure actually exists in language model, and how robust it is and how interpretable it is. And this is what we will show in the following sections. So for training the safety polytope, we need in general 3 steps. First, one need to obtain the labeled data set of features and safety labels. So we at least need to know what features represents which data and whether they are safe or not. And the second step, based on the data and the safety label, one can learn the parameters that define the polytope. And the third step is to use the polytope to steer unsafe to safe. So one can basically, the easiest way to check whether this polytope structure exists in language model is to just train it and see how accurate it is, and to know whether it has captured actually meaningful semantic representations is just to see how well the steering performs, which we will elaborate later in the experiment section. But now let's take a closer look at these 3 steps. So first is about obtaining the labeled datasets. We have many datasets, like in toxicity, unethical datasets, or there are lots of datasets that has a combination of several sentences with their safety labels, whether this is safe or not, whether this is toxic or not. So that really comes with the datasets. And usually people obtain intermediate layer activation as an input data's features. So for example, a language model, it can have 30 layers. And the intermediate layer activation means maybe you can stop an input propagation process and get the activation from layer 25. And typically people take it from the last token because the language model has the ability to do the next token prediction. So usually the feature, the activation at the last token will contain sufficient information for predicting the next token. And people use this as an intuition to roughly obtain the features of an input data sentence. And for this original data set, so sentence and safety labels, one can obtain this from normal ethical data sets, but can also obtain it from the labeled adversarial attack data sets. So from many adversarial attack benchmarks, once one generates a response to the attack questions, the benchmark will provide another large language model to check whether the response is successful jailbreak or not. And so usually for people can also use that model's prediction roughly as the safety label here. Okay, so that's the first step. The second step is to learn the polytope itself. So throughout the history of machine learning, there are general 2 schools of learning the polytope. One is through identifying vertices. So these are the intersection points of different linear constraints here. So one school of thought is to first recognize these vertices and then calculate and then define out what is the phi xi that's defining the polytope. But they are computationally very expensive. So for example, the quick Hall algorithm scales exponentially with feature dimension. So for large language models, this can go to a few thousand, or even if you are operating within the sparse autoencoder space, this can go to a few dozen thousand of dimension. And this becomes very computationally expensive, almost impossible. But there's another school of thoughts which learns each edge that I will, each facet that I will explain further. So we use the algorithm called convex polytope machine algorithm from this paper from about 10 years ago. So we will decouple this loss in a bit, but to give you a very high level idea, what it tries to learn is for safe data to have negative violations. And for any unsafe data, it should have positive violations, which I think makes sense to most of you here. So then people can use 0 as the decision boundary. Everything negative is safe, everything positive is unsafe. Okay. Then let's look at this loss function bit by bit. So the first term here, which says we only look at data that's inside the polytope, which is defined by this I+1. It basically says any data that's labeled with +1 inside the polytope. Safe data in our definition. So for these safe data, we calculate the violation here. This is the main thing that's calculating the violation. Kappa is a hyperparameter one can tune. It's a fixed positive number here. It's a margin, but one can tune. So in general, if a data is safe, the violation should be negative. And hopefully this whole expression should be negative. And this plus, bracket plus, means taking the non-negative of any function. So basically what it's saying that if anything within the brackets here turns out to be positive, we want to penalize that because it's a loss. So if it's normal, if the polytope is performing as expected, this should be 0 because no safe data should have positive violations. Okay, so far it makes sense. And now we also want this to stay true for all the polytope facets, because for a safe data, it shouldn't violate any constraints. So all the constraints needs to be satisfied. And now let's look at the second term, which is the other half of our data set, the unsafe data. For unsafe data, we label it as I-1, and we want it to be outside of the polytope. And unsafe data should have positive violations. So here it's a trick that people, because we want to minimize the loss, right? We negate this violation with some margin. So if something originally is positive, after adding this minus sign, it should be very negative in theory, like in the ideal case. And then again, people apply this bracket plus operation, this function, taking the non-negative side of it, and say that anything appears to be positive should be penalized. This again follows the intuition that all the unsafe data should be positive. After negating it, everything that's remaining to be positive should be penalized. That's the loss function. And there is a small design here of ZH, because for an unsafe data, it should violate at least one constraint. It could violate multiple constraints, but it should violate at least one. So in the convex polytope machine paper, they use this ZH, apply some heuristics to avoid the polytope collapsing into just one linear decision boundary. I won't go into too much details here about their heuristics, but basically it's more like an implementation thing. One can look it up in the paper. But generally, the second term means I want all the unsafe data to have positive violations. So I will penalize anything that's opposite of it. And the last term is a regularization term. Okay. If it doesn't make sense to you or it's too fast, just remember this green box. We want safe data to have negative violations and unsafe data to have positive violations. Yeah. And we also introduce a concept encoder. Why? Because we asked the question, does raw activations necessarily provide all the information or the clean enough information for the polytope to be learned as a feature. And in the feature space, it's possible to learn things from the raw activations, but also from an encoded features. So we mostly introduce this concept encoder for interpretability and robustness purpose, as we will see in the experiment section later. And this design is inspired by the sparse autoencoders, which is just one linear layer plus ReLU, and it transformed the dataset from the raw activations to encoded features and labels. So it's not a substantial change, just one layer, but we will see from the experiments that this significantly improves the performance. So on the graph, it looks like raw activations. You go through a concept encoder, you get the encoded features, and then you train the safety polytope. That's the inference process. Okay. And now let's combine everything together. The format is still similar with before. The goal is, again, for safe data to be negative violations and unsafe data to have positive violations, which is this loss. We just slightly changed the constraint violation to include the psi parameter that's not really used from the 10 years ago convex polytope machine paper, but the core idea is still the same. We want to achieve whatever we want from this green box, and we add a little bit of extra regularization term for the encoder that we just introduced, but the core idea stays the same. Okay, now that we have learned the polytope's parameters, we can use it for steering. And the steering part is also very simple. Once you have something, you can think about it as doing just a linear projection onto a space. Computationally, this is very, very fast. It's just doing a few steps of gradient updates. So during the inference time, this is not significantly increasing your latency. So what we do is that we try to minimize changes to the raw activations that we take from the language model, such that the polytope constraint is satisfied. So one can very quickly combine these two terms from Lagrangian relaxation. And because this whole polytope constraint loss, this computation is fully differentiable, one can just do it very quickly in a few steps. And here is a summary of the whole algorithm. We take the raw data, the sentence inputs, and we obtain the raw activations of a sentence. Then we check with the polytope whether this raw activation satisfies the polytope constraint. If the polytope is not happy about it, do a quick projection onto it and modify the raw activations. And then we override the activations at layer L, decode the next token, and continue. So this is the whole algorithm. Okay, I hope so far it makes sense for people. If you have any questions, because now I can't see any questions coming from the comments, but I guess I'll take them later. Okay, so now let's look at the experiment results. We first look at mostly through the adversarial attack lens, because in adversarial attack, the successful attack and non-successful attack is relatively easier to tell. And we can also observe the steering process, because if a sentence originally would be a successful jailbreak for a model, and after the steering, it becomes not successful, then it shows the success of the steering. So here are some results. We take the attack success rate, which is the percentage where an algorithm successfully induce a language model to say bad things. And here, all of these data points are averaged over 9 algorithms and repeated over 5 seeds. Some of them are very straightforward, like directly request. Some of them are state-of-the-art adaptive attack, for example. And the x-axis is the success rate, attack success rate. So the lower, the better. And the y-axis is the MMLU accuracy. So we roughly use that to represent capability. But in the paper, we have some more capability data set evaluation results. But for now, let's just look at MMLU as a metric. So the higher, the better, because it's accuracy. And so generally, you want your model to stay in the upper quadrant here. So for example, for Mistral 8B, the original model has an attack success rate of 55%. So it's very weak when facing the adversarial attack. But after applying the safety polytope steering method, so first detect, if it's not happy, steer it. After the steering, the attack success rate drops to almost 0%. I think it's 3 or 5 on average. And at the same time, it's keeping the original MMLU accuracy, performance accuracy. And this has happened similarly with Llama and Quen as well. So here, one very interesting result that we also get is by comparing it with MLP, multi-layer perceptron, because one can also think about a much, much easier version of this whole algorithm, where you just replace the polytope by an MLP. So during the classification stage, because you have safe and unsafe data, you can train an MLP with cross-entropy loss for classification. And then you can use this MLP, trained MLP, for steering using exactly the same method. So we compare the difference. So this MLP here has the same amount of parameters as the polytope. And this MLP plus 5 means we add even 5 more layers. So make it deeper and even more parameters. So we train polytope and MLP models to have roughly similar amount of level of classification accuracy for safe and unsafe data. So here we didn't optimize it too much because we also don't want it to overfit the data. We want to keep it still kind of robust, but being able to tell the difference, but not too much over optimized. Even though they have very similar classification accuracy, MLP and MLP with 5 more layers perform significantly worse than polytope. So this difference actually tells us that it's not only about your way of classifying safe from unsafe, but it's also about the representation you actually learn to ensure that the steering actually works. And here is another interesting data point, which is the rejection sampling, because someone can also ask, okay, so now we have a model that's performing very well, almost 90% of accuracy of telling safe from unsafe. What if we just use it to reject a model for all? So if we identify anything unsafe, we just reject it. Then we don't deal with the messy steering this MLP has in terms of difference with the safety polytope. But actually, if one does this rejection sampling, it can also lead to over-rejection. So in MMLU for Mistral, we use this rejection sampling, we use the same polytope training, same polytope model here. But instead of steering, we just do rejection. It achieves perfect attack success rate, 0, but its MMLU accuracy also drops significantly. So that is about the defense from adversarial attack perspective. And we also do a bit of ablation studies, as previously discussed. Why do we need the context encoder at all? It's because we notice that not all of the role activations in the model space are most suitable for polytope classification and for steering. So for Quen 2, for example, its activation space is probably already clean enough. But for Llama 2 and for Mistral 8B, without the context encoder, the polytope performs much, much, much worse. And just with that one linear layer plus ReLU, it can compress it can reduce the attack success rate to very, very low, almost perfect performance here. And here is another angle of looking at the context encoder, and also touch upon a bit upon the interpretability side of this work. So we try to understand to what extent this context encoder helps with interpretability. And because we have this many polytope facets, if any of them are actually helpful for us for understanding the semantic meanings from a data set. So for this set of experiments, we use the Beaver-Tails dataset. So this is a dataset with about 300,000 sentences, some safe, some unsafe. And for the unsafe data, it's categorized into 14 categories, ranging from animal abuse, child abuse, to financial crime, terrorism, violence, etc. So there are 13 categories of each different unsafe sentence. And what we do is we calculate the mutual information between each facet with the category. So this basically means if we only have this facet, how well is this facet able to tell the safe and unsafe difference from this category? Let's say for this category 0, animal harm. The facet number 34 has very good prediction, or its prediction has pretty much aligned with the label from this category, from animal harm. And so for without learning the polytope without a context encoder, one can see the edges, the facets are, one facet can capture way too many safety meanings, semantic meanings. So for example, this facet number 36, it's aligned with many harmful categories. Whereas once we apply the context encoder, the facets seem to be able to focus more about each specific semantic safety categories. And so how we generate these two is we calculate the mutual information between each facet with the categories, and then we do a pairing algorithm. So this is very fast to implement from the traditional, like the algorithm literature, the pairing algorithm, which tries to draw out this this diagonal axis. Okay, so we see a much more clearly separated facets encoding of the true categories. And here we do a bit further analysis of it, because for each facet, you can calculate the difference before and after you mask out certain context within the data set. For example, this is a violence data set which has different violence types. And for each facet, we go through all its predictions before and after masking out certain type of violence. So for example, facet number 7, it has the biggest KL divergence in its prediction, so the biggest changes before and after masking out kidnap context, but not on others. In facet 26, it has the most difference in prediction before and after we mask out the bullying context, maybe a little bit of killing context, but not on others. So this is also a different way of understanding what concept each facet captured. Okay, and finally, this is some ablation on the number of facets one should configure for a polytope. So generally, for adversarial attack, having one facet, so basically you train an SVM, is less ideal than having a little bit more facets, but they plateau as when you increase the number here. And this is also the same story with the Beaver-Tails. When you have only one facet, then SVM, you train an SVM for the classification, it performs a bit worse than when you have 20, let's say. Okay, So now let's go to the final section, which is the limitations and future work. Here I would like to discuss with people here maybe about potential next steps one can develop on top of the safety polytope method. So first, limitations. So one thing with my collaborator, we tried a little bit is exploring the theoretical aspects of the safety in language model. But we decided to not go very deep into it. We included a bit of the discussion in the last page of the paper, which is a bit of the learning theory of the polytope, around the polytope. But I think ideally, a good safety paper should also include some convincing theoretical aspects, which could be one of the future works to develop. And the second thing is more of an empirical observation. So on some data, let's say adversarial attack data from AutoDAM, this attack algorithm, we noticed that after the polytope steering, it could generate some semantically incoherent outputs. We think this is mostly because during our experiment, we only trained it on adversarial data. So on adversarial data, there are a lot of weird suffixes. And this could induce the language model to also say some nonsensical things, like how the suffixes are generated. And one potential fix is to train the polytope on the normal data too, to make it even more secure, more robust towards the normal data. But having said this, we also evaluated the polytope model on empty bench, which we include the results in the appendix. So at least on empty bench evaluation, it doesn't harm the performance too much. It's just some non-ideal thing we observe, but we think it's also fixable. Okay. And now it comes for the future work. The first thing I'm personally curious is to what extent it connects with the linear probes literature. So for people who don't know about linear probes, basically it's saying that once we have some data that are labeled as, let's say, honest, and some data we label as deceptive, one can train a linear classifier to distinguish these two. And based on that classifier, one can do steering. So this whole structure is very similar with the polytope algorithm, where we first learn a decision boundary, and then we try to manipulate model behavior around that learned decision boundary. The difference is polytope is fully unsupervised. So when we train it, we only tell it whether it's safe or not, but we don't tell what specific safety category it belongs to, such as deception, violence, or fraud, etc. It's mostly relying on automatic concept discovery. And I would say it's probably not necessarily accurate just because it's fully unsupervised. We don't necessarily know if the learned facets are actually extremely clean. At least I don't expect any unsupervised method to perform as clean or as strong as a supervised method. I think it makes sense for people. And for linear probes, they really rely on labeled data. So you really need the data to already be labeled, whether it's honest or not. But it's not necessarily robust. So I haven't seen too much studies on adversarially attack linear probes, but I don't expect it to be too difficult. So polytope is more robust, but unsupervised, maybe unclean in the learned directions. And linear probes is clean, but not necessarily robust. And what's potentially a combination of them? Can a combination of them combine the pros of both methods? I'm quite curious. And also I see there are lots of potential other studies by applying linear probes on polytope. Okay, so that's one future work. And another one is also interesting to study adversarial attack based on polytope. So we did all this time, we did steering something from unsafe to safe. And we do the reverse to steer something from safe to unsafe. I think on the algorithm side, on the implementation side, this is very easy. You just do the reverse of thing. But the main question is, how meaningful are the attacks? Does this model editing method just still make the model output gibberish things or nonsensical things? And how capable it makes the model to be? This is another question one can ask or one can study. And the last future work is more straightforward, which is to apply the polytope method onto various other undesired behaviors. Because essentially this is a framework, a safety framework. In my paper, we applied it to adversarial attack. We applied it on to some ethical data, but there are also many other undesired behaviors, such as deception, reward hacking, hallucination, etc. And it might be an interesting study to see to what extent polytope will be useful for these different settings. Okay, so to conclude, we introduce a robust and interpretable safety framework. And this is a geometric framework for safety. And we provide inference time steering without having to train anything. You don't need to fine tune the model. And hopefully you see the strong defense from it. And the facets can provide interpretable insights for further studies. The code is publicly available. You just need to you just search this paper, and in the end of introduction, you will see a link to the code. And it was published this year at ICML. Okay, so that is all I'm sharing today. And I am now open for any questions or discussions. Yeah.
Thank you, Cynthia, for the very nice talk. I think it went very great. So now if there are any questions, you can just open up your microphone and speak, or you can write, better if you speak. Okay, Fabio.
Hey, hello. Okay, I was trying to open the camera. And hi, Cynthia. Thank you so much for the nice presentation. And I was curious about one fact that you mentioned before. Basically, you said that using multiple layer perceptrons achieves worst results. And do you think this is due to the fact that the projection stage or the projection problem is more difficult, or maybe because of the boundaries learned by the MLP are different, not suited? So I was curious to ask this.
Yeah, thank you for the question. Yes, thank you. I personally lean towards the latter explanation. So maybe the learned decision boundary isn't so meaningful for it to fully reject the unsafe, the jailbreak strings. I think for the optimization side, this shouldn't be a problem for gradient descent. I think large language model has showed us how gradient descent is powerful. And it's also not very difficult to optimize through an MLP. So what you do is you modify the MLP input such that at the end of it, it will say this thing is safe. And I think this is very, very similar to many adversarial attack algorithms in the past. And I think the adversarial attack field has already told us this is a very, very strong optimization performance.
Okay, so thanks. So in short, the answer is the boundaries may be the problem and not the projection method that is quite similar to others. Okay, thank you a lot.
Thank you.
Yes, we have another question from Ting Wen. Go ahead, please.
Hi, Cynthia. Thank you for the talk today. It was very interesting. I'm curious about what's the motivation behind the use of polytope, and what do you think the advantage of it is, instead of or compared to other structures that or algorithms that is also available for learning a binary boundary? Yeah, thank you.
Yeah. Thank you for the question. Yeah, the motivation part, I think I briefly covered it in the beginning of my talk. So there are two aspects. One is the theoretical side. If you see language model generation process as a constrained MDP, then from the theoretical reinforcement learning literature, one can say that the safe features are captured in the polytope. This is theoretically proved in the reinforcement learning literature. And on the empirical side, if you have linear representation hypothesis, if you adopt this linear representation hypothesis thing, which is already shown in many previous paper, then you define a direction vector and you define a threshold. That's basically the definition of a polytope. So if something that has good theoretical foundation, so it's not something that completely doesn't make sense completely, it has a very strong theoretical motivation and a very strong empirical motivation. Why not combine them, and like why not just test whether this is also something useful, right? So this is the motivation of ever looking at the polytope. And why do we use it on top of other steering method or like models such as MLP? I think I have also explained it during the robust defense slides, that just by using an MLP, probably it doesn't learn a good enough decision boundary. And so that's why maybe a different geometric structure can really give you the more meaningful semantic changes when you do the activation steering. Yeah, I hope this answers your question.
Yeah, thank you.
Thank you.
Is there any other question?
I do.
Oh, maybe one more thing to add.
Yeah.
Oh, sorry.
No, go ahead.
Answer Tim Wen's question from before. Another motivation for polytope, for using polytope, is because it's such a simple structure. And then if one wants to do any theoretical things, it's much easier to do if you have a simpler geometric structure than a very complicated MLP. Just having one layer, like one polytope structure, or maybe with one other layer, the concept encoder layer, it's still possible to do some theoretical stuff. But if you have too many layers, like an actual MLP, it becomes much harder for anyone to do any meaningful theoretical derivations. So that's another motivation. Sorry, Raphael, I think I cut you off a little bit.
Yeah, no worries. No, yeah, I was wondering, maybe I didn't catch it during the presentation, but my question was like, where are you applying the defense in the architecture, like deeper layers or on the last layers?
It's on the layer that's the activation is trained on. So normally we take, let's say, layer 20 out of 25 layers, or 25. So somewhere from the middle to the end layers. This is mostly a heuristics people did in the past.
I see. How you choose the perfect layer, the best layer, based on a heuristic?
It's more like a It's more like a hyperparameter tuning on which layer you are choosing. So this layer number one can tune a bit. But I think the heuristic from all the past papers that I've read, people mostly just choose something from middle to end, and usually it can already perform pretty well.
Okay, thank you.
Any other question from the audience? Okay, if there are no other questions, I have just one curiosity, which was, I'm just curious to know, what is your opinion on, the kind of research direction which somehow conjectures that refusal is mediated by a single direction, right? Because, I mean, implicitly somehow by having a lot of facets in your polytopes, you are somehow implying that also safety is multifaceted, right? So I just wanted to have your opinion on that.
Yeah, that's a very good question. I also encountered this before, but I think the biggest difference is the polytope direction learning is all fully unsupervised, and that might be a big difference because for mediating refusal direction or in general many linear probes training, you have fully well labeled safe and like refusal or not their data. And the polytope training, we kind of know which data is safe, which might mean it's a refusal. But this is not as explicit as we provided for. And also, I think from the linear representation hypothesis, maybe the idea of refusal is just adding sorry to whatever answers you're giving. But where are you steering from that to that sorry? I think it's also worth investigating. For example, is it because of detecting violence that you say sorry, or you're detecting abusive content that you say sorry? And how does that add to the final rejection vector for sorry? This is also similar to the idea of safety. If we I don't know if there exists one vector that means safety. That would basically solve all the problems that we currently have. We just add this safety vector on everything and this problem is solved. But within safety, there are also many subcategories of concepts like no fraud, no toxic, non-toxic, ethical, whatever. And if each of those are a linear vector, how do they aggregate to be one safety vector? It's a little bit not straightforward for me to think about it in this way. Yeah, but anyway, this is a lot about other related thing, but directly answer your question about rejection mediated by one vector. I think it's because polytope is unsupervised in this sense.
Yeah, thank you
in
for
the categories sense.
Yeah, no, it's very interesting because actually this subcategorical problem that you mentioned is something which is real. So I just read, I think it was an ICML paper that somehow tried to encode refusal with a single direction and then have like kind of orthogonal directions, still mediating refusal, but in different kind of aspects. So like what you say, toxicity, harmfulness, maybe. So yeah, I think it's an open problem and an interesting one as well.
Yeah, definitely.
Okay, is there any other question from the audience? Okay, looks like no. So thank you, Cynthia, again. Maybe we can stop the recording now.
Yeah, I'm gonna stop the recording.
Thank you so much.
Thank you, Cynthia.
Thank you for inviting me here. Yeah, thank you.
Thank you, our pleasure.